Hi, well, it's Stephen Neshaba, and I'm here to help you out with one of the additional problems in the homework. And this one has to do with the cyclic process. The idea is that we start off with a perfect gas at that temperature, and it'll first undergo an isochoric cooling, so it passes down to a lower temperature. And step B was that it undergoes this isothermal expansion all along this line, is characterized by T2. And once we get out to the second volume, from V1 to V2, then it will undergo this adiabatic compression back to its original state. I've labeled this as pressure or P external because this is a reversible process. Then the P external is always pretty close to the internal pressure throughout. Now, there's just a couple of laws that we'll be using for this. One is first law, delta U equals Q plus W. And the second one I've just laid out here is the differentially create equation of state for the internal energy, CV dt plus pi sub t dV. And since we're dealing with the perfect gas, then I know that that's pi sub t is 0, so we only have to worry about that first term. So let's just get started here. For the first step, this isochoric cooling, I know that since it's isochoric, there's no change in the volume, so that means the work is 0. And let's see, I think I can write down what delta U is, because delta U is just the change, proportional change to the change in the temperature, so that would be CV delta T. Now, in order to say that, we've had to say that the heat capacity is constant. It doesn't depend on the temperature. So, okay, and let's see, I can figure out one more thing here, because if delta U is CV dt and the work is 0, then the first law tells me that this is also CV delta T. Now I'm using a convention here that delta T equals T2 minus T1. T2 minus T1. Okay, so that's step A. Now let's think about step B. This is this isothermal expansion along the T2 isotherm. And we have a few things that we can write down right off the bat for that. Since it's isothermal, I know that there's no change in U. And let's see, I can write down either one of these, because once I write down one, I know the other. And what we've seen previously is that the heat that goes into a perfect gas when it's undergoing a reversible isothermal expansion is nRT times the natural log of the volumes that change, and that would be V2 minus V1, V2 over V1. Okay, so we got that, and again, since delta U is 0, I know that that's just equal to minus Q for that step. And okay, so now we have the return trip that's going on an adiabat, a reversible adiabat, back to the original state. Since it's adiabatic, then I can write down Q is 0 right off the bat, and now I need to figure out one of these two. Well, I can do the same kind of trick here, can't I? Because I know that I'm changing the temperature. The change in U only depends on the change in temperature, so that's going to be CV delta T. But now this delta T is going to be the reverse. It's going from T2 to T1. So I'm just going to, if I stick with this, it would be a CV times minus delta T. So I'll put a minus sign up there. Well, when again, delta T is defined as being T2 minus T1. And since delta U is equal to Q plus W, that must mean also CV delta T with a minus sign in front. Okay, well, I've got all three steps, and I'm in a position now to add them all up. Let's get something that should be pretty straightforward. The total change in U, I can even anticipate it must be 0, because I've, after all, returned the gas to its initial state. And does that work out? Sure, CV delta T minus CV delta T, so that really does end up being 0. And let's see, how about the Q? Well, that's going to be the sum of these two terms, CV delta T plus that term. I'll go ahead and write it down. CV delta T plus nRT log V2 over V1. Okay, and well, we see that this is just the negative of that. I'm just going to write this as minus Q. But of course, that would have to have been anyway because delta U is 0. And so there we have all the math that's associated with it. There's one more piece to the problem. Do we think that the net work is positive or negative? And that all depends on the sign of Q here. But you can just figure it out from the indicator diagram. Let me argue it this way. No work done in the first step. The system did work on the surroundings. It did this much work. That's underneath this graph. Okay. That's how much work the system did on the surroundings. But then on the return trip, the amount of work that the surroundings did on the system was all this area, okay, with the opposite sign, positive work there. So obviously the positive work that was done during the compression is bigger than the negative of the work that was done during the expansion. And in fact, graphically, we can see that the total amount of work must be the area inside that closed circle. And we can just see from all that the total net work must be positive. Okay.